In the sun, hydrogen fuses together to form helium. But that's a little confusing because how out of only protons do we create a helium nucleus which has 2 protons and 2 neutrons? Well, the thing is, when the first two smash together, one of the protons actually emits a positron and a neutrino and quickly becomes a neutron. Next thing that happens is another proton smashes in. And again, we get more energy released. Now, if two particles like this collide, they emit 2 protons, and what we're left with is the helium-4 nucleus. There you have hydrogen fused into helium. And a lot of mass lost, a lot of energy released.
The Sun and Earth both emit electromagnetic radiation. This movie will help you describe the differences between the types of radiation emitted by the Sun and the Earth. Electromagnetic radiation is energy that travels in the form of electromagnetic waves. Different types of electromagnetic waves carry different amounts of energy. The shorter the wavelength, the more energy carried by the wave. The wavelength of emitted radiation is determined by the temperature of the object it comes from. The higher the temperature, the shorter the wavelength of emitted radiation. The Sun, with its high surface temperature, emits a great deal of high-energy, short wavelength radiation. Energy emitted by the Sun is also referred to as solar or shortwave radiation.
Radiation is energy emitted by an object, like light from a light bulb. Radiation happens at different wavelengths. The hotter the object is, the more energy it radiates at shorter wavelengths, from longest radio waves to shortest, highest energy gamma rays. Light bulbs can be used to illustrate the solar radiation that reaches Earth. Although the Sun's peak output is at visible wavelengths, most solar energy reaches us as infrared radiation that we feel as heat. Think of the night lamp in a reptile cage. Next, we get hotter, higher energy shortwave radiation that we see as visible light and different colors at different wavelengths. A lesser amount of even higher energy ultraviolet radiation reaches us. Think of black lights and tanning beds. We can't see or feel UV radiation except by the damage it causes, such as sunburn and fading fabric. Luckily, our atmosphere protects us. In the stratosphere higher than Mount Everest, a gas called ozone acts like sunscreen and filters out most UV radiation so that even less reaches us at the surface. Most energy on Earth comes from solar radiation. We see the fraction that reaches Earth as visible light, we feel the infrared portion as heat, and we notice the harmful ultraviolet rays when we get a sunburn. For more information, visit climatebits.umd.edu.
Conduction, convection, and radiation. Conductive heat transfer is what happens in this picture. When heat is transferred along the handle of the pot, this heat is transferred between atoms in contact with each other. In a solid, molecules transfer vibrational energy physically to their bonded neighbors. Imagine linking arms with everyone in the class, so you're trapped in a solid form, and then try to transfer energy just by bouncing in place. Conduction also happens in liquids and gases. In these cases, heat or kinetic energy is transferred during collisions. Convective heat transfer is a much more efficient method of heat transfer for gases and liquids. During convection, millions of molecules of gas or liquid transport heat quickly by diffusion or currents. For example, in this image you can see that at the bottom of the pot, heat is conducted by the hot surface to the water at that hot surface. That heat makes that water expand and become less dense. That water then rises to the top of the pot, displacing the colder, denser water at the surface, which then sinks to the bottom and is heated by the conductive pot. Through this process, the heat is rapidly convected through the entire fluid in a continuous cycle. During radiation heat transfer, electromagnetic waves are released from a hot source and spread outwards through space in all directions. When those waves collide with other objects, they excite the molecules in those objects and raise their temperature. Heat is radiated from all objects with a temperature, that is, from all objects whose molecules have any internal kinetic energy at all. Thermal radiation is generated when heat, from the movement of charged particles within the atoms, is converted to electromagnetic radiation. This image shows, and we know from personal experience, the radiative heat that's transferred from a hot fire to the objects around it. In this image, we see the hot fire radiating heat outwards. The bottom metal of the pot picks up some of that radiation and heats up. That heat is then conducted through the pot to the water in contact with it. The water molecules within the pot mix with each other and transfer heat evenly within by convection.
Light. It is nothing but a form of radiant energy. When light falls on a body, it may either be absorbed, it may be reflected, or it may be transmitted through, when light travels through a medium like air and then encounters another solid or liquid medium like a man, a car, a book, or even water surface, most of the light, after interacting with the boundary separating the two medium, comes back to the first medium. This phenomena is called reflection of light. So in other words, reflection of light means that light waves are neither transmitted through nor absorbed, but are bounced back from the surface of the medium that they encounter. The ray of light approaching a reflecting surface, such as a mirror, is called incident ray, and the one that bounces back is called the reflected ray. An imaginary line drawn from the point at which the incident ray strikes and perpendicular to the reflecting surface is called the normal. The angle between the incident ray and the normal is called the angle of incidence, and the angle between the reflected ray and the normal is called the angle of reflection.
Light is corresponds to a specific energy. So light travels in quantized packets in photons, and the energy of a photon is inversely proportional to the wavelength, right? So if I have shorter wavelengths, they have higher energy. If I have longer wavelengths, they have less energy. So if I think just about the visible part of the spectrum, violet, blue, these are high energy wavelengths. Red is a low energy wavelength. So right below visible spectrum, I have IR. Right above the visible spectrum, I have UV. Okay, so that's key, right? Because we're thinking about how does
conducting thermal energy. Something you should note, in general, metals are excellent conductors, while plastics, wood, and fluffy materials are pretty awful conductors. So metals, great conductors, and I'm going to explain why. A metal, if you were to look at it very microscopically, like at the atomic level, you would see that metals are really close together. The atoms are really closely and tightly packed together. And gases, on the other hand, are really spread out. So my gas is going to be kind of like all spread out across the screen here. And so if we were transferring thermal energy into this metal, this is our metal on the bottom here. If we were to transfer thermal energy to one side of it, then that particle would absorb the energy, almost like kicking a soccer ball, you know? And then that particle would transfer to this particle, and this particle, and then this particle, and it would go right on down the line, kind of like Newton's cradle, you know, those little balls that go back and forth. That's exactly what's sort of happening here, and that's why metals are great conductors, is because the particles are so close together. Whereas in a gas, they're not close together. So if I were to transfer thermal energy into this particle, then it would probably like bounce into this one, and then this one maybe, and then it would go way over here. Who knows? You know, just since they're all spread apart, it takes a long time for the thermal energy to transfer through them. So in general, metals, great conductors, gases, not so much. And I put a few examples here to illustrate this for you. One being a toaster. If we want our toast to get hot, we're going to run the electricity, the energy through some metal so that it transmits it to the toast. Excellent conductor inside of the toaster. This blacksmith probably was working on a piece of metal down here in the bottom left, and it's glowing hot. And blacksmiths have to wear super protective gloves, and they have to use tongs because even though this part of the rod is red hot, the thermal energy will transfer all the way up and travel up this rod into the opposite of conductors. They are poor conductors of thermal energy. They actually block thermal energy. They're kind of like a wall for thermal energy, which is kind of nice because we don't always want thermal energy to leave. We want to keep it and we want to use it. And so in the case of staying warm in the winter, you wear a jacket, which is made out of nice fluffy feathers, sometimes, or just some sort of fabric or whatever. But that fabric has a lot of air in it. It's very fluffy. Air is a poor conductor. It's a good insulator. And so that's why we wear jackets, to keep the heat inside of our bodies. Cardboard is also a good insulator. It's not amazing, but it's pretty good. And if you look a close picture of cardboard, you'll see that some cardboard is corrugated, meaning that it has these corrugations in them, or these little gaps, which is air. Air is a good insulator. So if we can make a structure that somehow has some air pockets in it, that's generally going to be a pretty good insulator. Wood is the same way, except you can't see it very well, but if you look at wood underneath a microscope, this is, I think, 200 nanometers or something like that, 200 nanometers or micrometers, very, very small, very, very zoomed in, but you can see that the wood has lots of little tubes going through it, lots of little spaces for air, and it makes it a very good, not a very good, but a good insulator, much more so than, say, like a chunk of metal. I mean, wood does not conduct nearly as good as metal. It's actually more of an insulator than it is a conductor.